We were discussing multiplying a vector by a scalar. Let's summarize. If A is a vector and S is a scalar, then by multiplying them together, we construct a new vector, B, where B will be parallel to A. The x component of B is found by taking S times the x component of A. The y component of B is found by taking S times the y component of A, and so on. And then the magnitude of B will be equal to the magnitude of S times the magnitude of A. Furthermore, if S happens to be less than 0, then B will be anti-parallel to A. They'll point in the opposite directions. So for instance, if B equals minus A, then the scalar S is -1, and A and B will be equal in magnitude but opposite in direction. All right, so adding vectors. We can multiply a vector by a scalar, but you can't add a scalar and a vector. They are two different things. They're not compatible with addition. It would be like trying to add kilograms to seconds. They're different things. You cannot do it, but you can add vectors together. So let's see here. Suppose we've got our vectors A and B that we've already defined. A equals 3i hat, B is -2j hat. And let's construct a new vector, C, by adding vectors A and B together. So A plus B will be 3i hat, plus B will give us -2j hat. Here's A, here's B, and this is the C that we get. A new vector pointing in a different direction from the original two, and with these components. So we see if C is 3i hat and -2j hat and no k hat component, then the components of C, Cx, Cy, and Cz are just 3 in the x hat direction, 3 in the I hat direction, -2 in the j hat direction, and 0 in the k hat direction. What we've done is obtain the new vector by adding our original vectors component-wise. We get the x component of the new vector by adding the x components of the original vectors, 3 and 0. There's 3 and 0 x component here. We get the new y component by adding the y components of the original vectors. So no y component. Here it's -2. And then we get likewise for the z component. There are no z components here. So we add them component-wise. And so our cx comes from ax plus bx, and our cy here comes from ay plus by. Let's go a little deeper here. We can add vectors in unit vector notation. We want to make use of this unit vector notation. So we've got this vector c now, which we could express this way. This is c expressed in unit vector notation, as opposed to this sort of parentheses with commas notation. We're not going to be using this notation for vectors anymore. We're going to be using the unit vectors. So we can write c as 3i hat -2j hat plus 0k hat. Okay, and I'm going to explicitly write 0k hat here, but normally if one of the components is 0, then we just leave it out. So we would normally write c as just 3i hat -2j hat. But for explicitness here, as we're introducing the topics, I'll include the plus 0 as well. But normally we would just not leave that part. It would be understood to be 0. Now, let's define two new vectors. Let's let D be -i hat plus 4j hat, and E will be 4i hat minus j hat. And understand that when we say -i hat or minus j hat, what we mean is -1 times I hat. And this would be -1 times j hat. So this would be those three vectors there, C, D, and E. I've left off the k hat components just because it's hard to draw in 3D here. What we want to find is a new vector f, which will be the sum of vectors c, d, and e. So we add them component-wise. In unit vector notation, that looks like this. Here is c, 3i hat -2j hat plus 0k hat. Here is d, -i hat plus 4j hat plus 0k hat. And then here is e. And if we line the three vectors up, c, d, and e, we just simply add down the column. Add all the x components, add the y components, and add the z components. So 3 minus 1 plus 4 is 6. Minus 2 plus 4 minus 1 is plus 1, and then zeros. So here is the sum of those three vectors. F is 6i hat plus j hat. That's the vector F. What does it look like? We can add graphically using two different methods. First, the head to tail method. You can add any number of vectors together with this head to tail method. Here we have three vectors to add, c plus d plus e. Here's how you do it. You start by drawing one of the vectors and then take another one. So I drew c, then take d and draw d with the tail of d at the head of c. This is the tail of a vector. The arrow part is the head of the vector. So put the tail of d at the head of c, draw it in, and then add in your next vector. Put the tail of e at the head of d. So we sort of make this chain of vectors. And you can do it in any order. So we could start with c, then do d, then do e, or we could have started with d, then done c, then done e. The answer comes out the same either way, because we know, of course, by the commutative property of addition that c plus d plus e is the same thing as c plus e plus d, or d plus c plus e. So the order of them won't matter. You can convince yourself by trying it a few different ways graphically. Anyway, you construct this chain of the vectors, lining them up all head to tail, and then the result, the sum of the three of them, can be found by drawing in a vector from the very beginning of the chain to the very end of the chain, from the tail of the very first vector to the head of the very last vector. Draw in that vector there, and that will represent F. C plus D plus E. This is our vector F. And note it has 6, its x component is 6 units, and its y component is 1 unit. That matches what we got here. 6i hat plus 1 j hat. That is vector F. So there's our head to tail method to visualize the new vector we get by adding C plus D plus E. Just make that chain. There's a second method, the parallelogram method. In contrast to the head to tail method, where you can add any number of vectors together, your chain can be of any length. In the parallelogram method, you have to take your vectors 2 at a time. That's a bit more limiting, but we'll also see that there is some usefulness to the parallelogram method. So 2 at a time. I want to add C plus D plus E. I'll start by adding C plus D. Here, you put the vectors tail to tail. Put their tails together and have the heads pointing away from that point. Then, let these two vectors be two sides of a parallelogram. So we want to draw in the other missing two sides of a parallelogram. So there'll be a side parallel to D, and then we'll put in a side parallel to C. So we draw that parallelogram, and then the sum of C plus D will be a new vector pointing from their tails to the opposite corner of the parallelogram. And that vector in pink there, that represents C plus D. Add those two vectors, and we'll get this vector. We see it could be expressed as it has 2 units in the x direction, 2 units in the y direction. So this would be 2 I hat plus 2 j hat. That's the sum of C plus D. But we also want to add in vector E. So we repeat. We take our new vector, C plus D, and put that tail to tail with the third vector, E. And once again, draw a parallelogram. So make these two the sides of a parallelogram. We need another side that will be parallel to C plus D. And then a side that's parallel to E. Draw in that parallelogram, and the sum of C plus D plus E will point from the corner where the tails are to the opposite corner of your parallelogram. So that vector in pink there, that is vector f. And you can see that it matches the vector f that we got from the head to tail method. So of course we get the same answer using either method. F here would be expressed as 6 I hat, 6 units in the x direction, plus j hat, 1 unit in the y direction. So we can only do 2 at a time with the parallelogram method, but the advantage is that this is the way we naturally draw free body diagrams. We always draw our forces in an FBD tail to tail like this. So an FBD is already kind of set up for you to do parallelogram method. Whereas head to tail method, you'd have to sort of break apart your free body diagram and draw this separate diagram to make a long chain here. So in summary, these two graphical methods for adding vectors. Head to tail method is best for adding 3 or more vectors. We can make a chain of vector 1 plus vector 2 plus vector 3, and then from the very beginning of the chain to the very end of the chain is the sum of the 3 vectors. Or parallelogram method, that's quickest if you have just 2 vectors to add, especially if you're in a free body diagram. If you have a free body diagram where the vectors are already tail to tail. So 1 plus 2 become the sides of a parallelogram. The sum of them points from this corner to the opposite corner.